We're adding a new set of functions to your toolkit. So same derivatives, same integrals like we've always talked about, we're just adding one more function that we can work with, or one more set of functions. We're going to be working with hyperbolic functions. The first one is called the hyperbolic sine, S-I-N-H, and it's pronounced sinh. The hyperbolic sine, or sinh, is a way that we can use to represent e to the x minus e to the minus x over 2. Now you might imagine that this is easier to work with than this if we're taking derivatives and integrating and combining these. We also have another one for cosh. Cosh is the hyperbolic cosine, and it's the same thing, it just differs by the plus sign in the middle. Now all of the formulas that you're going to want are in my math lab under the lectures, and it says hyperbolic functions formula sheet, so I will show you where that is real quick. Okay, so here we are. Here's our lecture videos right here. We're in Unit 1, and if you come down here to the bottom, this will be a hyperlink to the hyperbolic functions, and this is your hyperbolic functions formula sheet. So these are all the formulas that you're going to want to work on this assignment. You certainly don't want to write them all down, and you don't memorize them either. This formula sheet will be provided if needed. So these are the two that we just wrote up here. So what I'd like to do is to just jump right into taking derivatives and integrating, because it's really the same process. We just have a new set of formulas. We need to identify u's, du's, follow through with the formulas. So let's go ahead and try some problems. Let's start with derivatives. So the first one that I would like to look at is the derivative with respect to x of 9, and this is the sinh, hyperbolic sine of x over 5. So I want the derivative of the hyperbolic sine as the upshot. So what we'll want to do is look on your formula sheet and pull off the formula for the derivative of the hyperbolic sine. So let's pull that off the formula sheet. Now the formula sheet is assuming, that's a little fuzzy there, the formula sheet is assuming that the argument of your hyperbolic sine is just x. So we need to think about this a little bit different because ours is not just x. The hyperbolic sine of u, the derivative of the hyperbolic sine of u is cosh, the hyperbolic cosine of u du, or du dx, however you want to think about that. So it's just like our other regular derivatives we used to do. So the derivative of the sinh of u is the cosh of u prime. So what we want to do is the chain rule. So I drag the 9 along. The derivative of the sinh is the cosh of u times the derivative of the argument, or the derivative of u. So as we're writing this out, the cosh of x over 5, and then the derivative of x over 5 is 1/5. Pull the 1/5 out front, and I have 9/5 cosh x over 5. That's my derivative. So I have a different set of formulas, and I have to remember that if they just give me this in terms of x, I need to recall that if my argument is different than x, I have to tack on the u prime, or the du. I can combine all of these with things like product rule, quotient rule, chain rule. So none of those things change. All the other things that I can work with, they're just a new function to work with. So this one is the inverse, this is a mouthful, the inverse hyperbolic tangent. Okay, so inverse hyperbolic tangent. And I also have a product rule here. I have my first function and my second function. So let's go ahead and look at the formula sheet, and let's pull off the derivative of the inverse hyperbolic tangent function. Okay, so it's a little pixelated there. So when I start to take my derivative, I need to use the product rule. So the product rule says the first function times the derivative of the second function, and I'm just going to write it out right now, and our next step will actually take the derivative, plus the second function times the derivative with respect to theta of my first function. So that's the product rule. That's Calc 1 product rule. Okay, so let's go ahead and do that now. Let's take 1 minus 4 theta. Now, what is the derivative of the hyperbolic tan? It's right here, but remember, my argument is not just an x or a theta, It's actually a function of 4 theta. So when I do this, the 4 theta goes here, quantity squared, and then I have to take the derivative with respect to theta of 4 theta of the argument. So keep that in mind. Okay, so let's do that. So the derivative of this piece right here is going to look like 1 over 1 minus 4 theta quantity squared times the derivative with respect to theta of 4 theta. So there's my chain. Okay, plus the inverse hyperbolic tan. And then the derivative of 1 is 0, and the derivative of negative 4 theta is negative 4. So let's go ahead and write this out. So this would be 1 minus 16 theta squared, and the derivative of 4 theta is 4. Minus 4, so I'm going to take this 4 and pull it over here. So minus 4 inverse hyperbolic tan of 4 theta. Now there's some simplification that we can do here. So it looks like I have 4 times 1 minus 4 theta all over 1 minus 16 theta squared, which is the difference of perfect squares, so it factors into 1 plus 16 theta, 1 minus 16 theta. And then this second piece, minus 4 inverse hyperbolic tangent of 4 theta. So here's 1 minus 4 theta. Oh, I'm sorry. That is 4 there. So square root of 16 is 4. So that factors into the difference of perfect squares of 1 plus 4 theta and 1 minus 4 theta. So these cancel. And I'm left with 4 over 1 minus 1 plus 4 theta minus 4 hyperbolic tangent of 4 theta. Okay, and that's my derivative. So that one we were able to simplify right here when I could factor this into a difference of perfect squares and do some canceling. So that's an example. Again, just if you have the formula, you're going to be fine, and you will have the formulas. I will never expect you to memorize these formulas. Let's look at one more derivative, and then we'll look at a couple integrals. The derivative here will be the derivative with respect to x of 14 inverse cosine of x minus 14x hyperbolic secant, the inverse hyperbolic secant of x. Okay, so there's a lot going on here, and we need a couple formulas. First of all, I need the derivative of the inverse cosine, and then I also need the derivative of the inverse hyperbolic secant. And as a quick heads up, I do have a product rule here. So let me go ahead and pull those two formulas onto the screen, and we will use those to help us out. Okay, let's start with the derivative of the inverse cosine of u. Now in this particular case, I just have, my u is just x, so this is pretty straightforward. So I'm going to have a 14, and then I have a negative u prime, the derivative of x is 1, over the square root of 1 minus x squared. So that's the derivative there. Now for this next piece, I have a product rule, and not only do I have a product rule, but I have a minus sign out front, so I need to make sure that I have the minus sign there so that the negative gets distributed correctly. Okay, so from here I'm going to have my first function times the derivative with respect to x of the inverse hyperbolic secant plus the second function, which is the inverse hyperbolic secant, times the derivative with respect to x of my first function. Okay, so this piece is done. It's right here. So I'm going to drag it along. Actually, I'm going to rewrite that as a minus 14 in the numerator. Square root of 1 minus x squared. And then here's my minus sign. I'm going to put that in red so we don't forget about it. Minus sign. And then let's go ahead and take that derivative. So 14x. And now I need the derivative of the inverse hyperbolic secant. Well, that's right over here. So I'm going to follow with this. And my argument is just x. So I can basically just copy this down because the argument here is x as well. So that's going to look like negative 1 x square root of 1 minus x squared. That makes sense. Secant is 1 over cosine, and this is cosine, so they are very similar. Okay, so plus the second times the derivative of 14. There should be a little x thrown in here. It's hard to see. And the derivative of 14x is 14. Okay, so let's go ahead and keep simplifying here. Dragging this along. I'm going to go ahead and distribute the negative. So this is going to be a plus 14x over x times the square root of 1 minus x squared. And this negative went here. Now it's going to come over here. So that's going to be minus 14 inverse hyperbolic secant of x. So these cancel. Whoops, not that. The x is what cancels here. And then we also have something else that cancels next. These two terms go to 0 after I cancel the x's, and this is my final answer. This is my derivative. Okay, so a lot of simplified there, and we would expect that to kind of happen just because we know that cosines and secants kind of go together. They're reciprocals of each other. Okay, let's go ahead and start with an integration problem. Let's look at the integral from negative natural log of 12 to negative natural log of 2. So this is a definite integral of 2 times e to the theta sinh of theta. Well, we don't have any formulas that relate any integrals like this that we've seen before. So my thought would be, let's use our definition of sinh and rewrite this. So let's recall that, and again, that's on that same formula sheet. So let's use the fact that the sinh of theta is going to be equal to e to the theta minus e to the minus theta all over 2. So let's rewrite this integral. So I have 2 e to the theta, and then the sinh would be e to the theta minus e to the minus theta all over 2. So most of this work is algebra. I see right away that the 2's cancel, and then I can take this e to the theta and distribute it, and let's see what we get there. Again, I still have my limits of integration. I have not integrated yet, even though it seems like I've done enough work. So I'm going to have e to the theta times e to the theta minus e to the theta times e to the minus theta d theta. That's what this is simplifying to. Again, this is not the integral yet. And I have my limits of integration. So when you multiply like bases, like e to the theta times e to the theta, that's going to be e to the 2 theta. And then this next one, e to the theta times e to the negative theta, theta minus theta is 0, so this is minus e to the 0. But e to the 0 is 1. Anything to the 0 power is 1. So that's e to the 2 theta minus 1 d theta. This looks a lot better than it did. So I think we're doing pretty good here. Let's go ahead and look at next steps. I'd like to split this up into 2 integrals just to make it easy to work with. So this is going to be the integral of e to the 2 theta d theta minus the integral of 1 d theta. So for here I'm going to use u substitution, good old u sub. If u is 2 theta, du is 2 d theta. So I'd have to multiply by a 2 on the inside, compensate with the 1/2 on the outside, so I'd end up 1/2 integral e to the u du. Well, the integral of e to the u is just e to the u, but in this case we know e to the u is 2 theta. Now over here the integral of 1 is just going to be our variable theta. So this is my integral, 1/2 e to the 2 theta minus theta. Now I'm going to evaluate this. So again, most of this has just been some algebra, so this is some more algebra we're going to put on here. Minus theta evaluated from negative natural log of 12 to negative natural log of 2. Okay, so 1/2 e to the 2 times negative natural log of 2 minus a negative natural log of 2. So that's my upper. I want to make sure I get brackets and parentheses in the right spots. And then my lower is going to be 1/2 e to the 2 times negative natural log of 12. Okay, that's my upper. And then we're going to do our lower minus a negative natural log of 12. So there is a lot of room for mistakes here with all the negative signs running around, so let's proceed with caution. Okay, so we'd have our 1/2 e, so then I'd have a negative 2 natural log of 2, okay, plus natural log of 2. So that's what I'm getting out of this bit right here. We'll simplify the next term next. So for our next term, I'm going to take the negative and distribute as well. So I'm going to have minus 1/2 e to the minus 2 natural log of 12. And then here I'll have a negative, negative, negative is a negative natural log of 12. So we're on a roll here. I see those negative exponents, so let's go ahead and think about simplifying those. So if I have those negative exponents, that would flip down into the denominator and I'd have 2 natural log of 2. And I'm going to go ahead and flip this one down and have them together. And then I'll have these natural logs over here together. Okay, now the 2 that's out front, I can pop that up top on both of these. So 1/2e to the natural log of 4 minus 1/2e to the natural log of 144. Okay, now let's look at this. So this is the difference of the logs. I can rewrite that as the quotient. Whoops, not 16, 12. Okay, now let's keep working. We know our shortcut here, e to the natural log of 4. Remember, this is log base e. You can think about those as canceling as just 4. And over here, this is 144. Because again, this e and this base we can rewrite just as the argument. And that would be plus natural log of 1/6. So this is going to be 1/8 minus 1/288 plus natural log of 1/6. And of course we can simplify a little further. So we'd want a common denominator here, and 8 goes into 288, 7 times 4, 8 times 3 is 24, so that would go 3, 8 times 3 is 24, so 36. So I'd multiply top and bottom by 36 here. And this would equal 36 minus 1 all over 288 plus natural log of 1/6. And then our last step, 36 minus 1 is 35 over 288 plus natural log of 1/6. Now we could actually simplify this a little bit more because the natural log of 1/6 could be broken up into natural log of 1 minus natural log of 6, and the natural log of 1 is 0. So we could actually rewrite this as 35 over 288 minus natural log of 6 as well. Just another rewrite, but this one works great. So step by step, the toughest part here was not the integration. The toughest part was the algebra. So keep track of things. Don't drop any signs. Frequently go back and check for errors. I know that happens to me a lot as I find a mistake. And if I can fix that mistake early, it's easier to continue on and not have to go back so far to fix your mistakes. We're going to do one more integral. So for this integral, we'll definitely need our formula sheet. And this is also a definite integral. Gives us some practice evaluating functions. Let's look at the integral from negative ln of 2/5 to 0 of the cosh squared of 5x over 2. Now this looks pretty straightforward, but you can see we're really going to get down in the weeds here when we end up actually evaluating this. So we're going to use a couple of formulas off of our formula sheet. So let me grab a screenshot of those and pull them in. Okay, this is the one we need for now. So what we're going to do is we don't have a way to directly integrate cosine squared or cosh squared, either one. I always have to use this double angle formula. So let's go ahead and rewrite using that. And I'm going to drop my limits of integration for now while I work through this, and then I'll pop them in at the end. Key is don't forget. So this would be cosh of 2 times my angle plus 1 all over 2. So that totally makes sense. So this angle goes from x to doubling. So my angle is a little different. So I'm going to take this and double that angle as well. That's why it's called the double angle formula. So I'm going to double that. And then I see that the 2's cancel here. So when I rewrite, I'm going to have the cosh of 5x plus 1 all over 2 dx. Now I'm going to want to integrate these, and I think I want to split them up into 2 separate integrals. So this would be 1/2 integral cosh of 5x dx plus 1/2 integral of 1 dx. So again, I pulled the 1/2 out front. It has to go to both of these though, so it has to be in front of both. So for here, u is equal to 5x, du is 5 dx. So I'm going to compensate with 5 on the inside and a 1/5 on the outside. So for that one I get 1/10 integral cosh of u du. And then my next one is pretty straightforward. The integral of 1/2 dx is going to be 1/2 x. So now we need the formula for the integral of cosh of u. Okay, so the integral of cosh of u is sinh of u. So this is going to be 1/10 sinh of u, and then this is still my 1/2 x, so I'm kind of dragging that along. Now, sinh of u, I have to go back. U was 5x, and there's my integral. Now, if this was an indefinite integral, I would be done, and I would just go ahead and put plus c on this. But I need to evaluate this, and I will evaluate this from what was it, minus ln of 2 over 5, because that was given up to 0. So let's go ahead and plug in the 0 first. So 1/10, this is my upper, sinh of 5 times 0 plus 1/2 times 0, that's my upper, minus my lower. Okay, this is where we got to be careful here because of that layered fraction. 5 times negative ln of 2 over 5 plus 1/2 x. In this case, that's minus ln of 2 over 5. Let's go ahead and simplify. So I have 1/10 sinh of 0 plus 0 minus 1/10 sinh, the 5's cancel here, of minus ln of 2. Okay, now let's double check our negative went here. Now it's going to come here. So that's going to be a negative times a positive times a negative is a negative 1/10 ln of 2. Okay, so again, the negative comes here. Negative times a negative is a positive. Whoops, good thing I double checked that. I had the wrong sign. Okay, so now we need to figure out what is the sinh of 0 and the sinh of negative ln of 2. Well, we're going to pull in a formula for that that is the definition of sinh. So let's go ahead and pull that in. So this says that everywhere there's an x, I go ahead and plug it in here to this formula. So rewriting, I have 1/10, and then sinh of 0 is going to be e to the 0 minus e to the minus 0 over 2. Okay, the plus 0 we can throw out here and not worry about it. And then for this next one, I'm going to have minus 1/10. This is going to e to the minus ln of 2 minus e to the minus a negative ln of 2 all over 2. And then I have this plus 1/10 ln of 2 here. I better not lose. Okay, simplifying further. E to the 0 is 1, e to the 0 is 1, And then I have this 1 over 20 out front if you want to look at it like that. Or if you wanted to, you could also flip the 10 down and rewrite this as a single large fraction, either however you want to do it. So if I look at this, I have minus e to the minus ln of 2 plus e to the positive ln of 2 all over 20. Now this negative has been distributed, so I need to fix up my signs here. I'd like to split this into two separate fractions. That would make me happier about the signs. So this would be 20, this would be 20. And then plus 1/10 ln of 2. So this term, 1 minus 1 is 0, goes to 0. And then here what I see is this will flip. So this is going to be a minus 1 over 20 e to the ln of 2. Okay, plus e to the ln of 2 over 20 plus 1/10 ln of 2. So what we want to have here is a common denominator, and I already have the 20. What I'm missing is e to the ln of 2 here. So e to the ln of 2. So rewriting, this is going to look like negative 1 over 20 e to the ln of 2 plus e to the ln of 2 times e to the ln of 2 all over 20e to the ln of 2. And this will get better in a minute. Don't give up. Plus 1/10 ln of 2. Okay, so e to the ln of 2 is just 2. So this is negative 1 times 20 times 2. This piece is also 20 times 2 in the denominator, but let's look at the numerator. This would be e to the ln of 2 times e to the ln of 2. When you multiply like bases, you add exponents. So this would be ln of 2 plus ln of 2 is 2 ln of 2. Okay, now that 2 that's in front of the ln can pop up top. So here I'm left with negative 1 over 40 plus e to the ln of 4, because 2 squared is 4, all over 40 plus 1/10 ln of 2. So the next thing here that I can look at is how to simplify that numerator. So I have a negative 1 over 40 plus 4 over 40, because remember we can think about this base canceling this base, and I'm left with 4, plus 1/10 ln of 2. So 4 minus 1 is 3 over 40 plus 1/10 ln of 2. Now there's different ways we could write that ln. I could pop that up and call it to the 1/10 power, or I could also call it the 10th root. But this is one of the simplifications that would work just fine. So lots of details, and most of it is just algebra, distributing the signs correctly, rewriting the exponents. So there's not a lot of problems in the homework set for this, not as many as usual, because they do take such time and attention to detail. So make sure you print out that formula sheet so you don't have to write down all the formulas. And if you need those formulas on an exam, they will be provided. If you have any questions, please let me know. I'm always happy to help. Good luck.